This is TurboVac 3, the third and final installment of my RC fan car series, and I think this one is going to be the absolute fastest. It's also the absolute ugliest. Look at how much better the other ones look. So today, let's see if we can actually build this thing to go faster than the 1.4 second 0 to 60 of the prior build. And then we're going to destroy this thing so I'm never tempted to touch it again because these fan cars are so annoying to deal with. We're also going to do a test with the fans backwards to see if it floats like a hovercraft. But first, we need to discuss the science behind acceleration. When it comes to 0 to 60 times, we are talking straight line acceleration, sometimes referred to as longitudinal acceleration. And this is critical for vehicles like top fuel dragsters, which are far and wide the fastest cars in the world when it comes to 0 to 60. But since this is also a road car, I actually care about lateral acceleration as well, which is where Formula 1 cars come in as the best in the world and top fuel dragsters are pretty much useless. After all, this build was inspired by old Formula 1 cars and other road cars. It was never actually intended to be a dragster. It can turn really fast. In this video, we're using 0 to 60 because it's the least sensitive measure to driver's skill, which I don't really have, first of all, and it's also the most direct measure of longitudinal acceleration. But I've also proven in other videos that this type of fan car platform can easily pull 3 Gs of lateral acceleration, which is absolutely mind-blowing for a toy car. When it comes to straight line acceleration, we really need 2 things. First is power and second is traction. Because a car is either power limited or it's traction limited. And in this case, we're starting out traction limited. With low speeds like 0 to 60, most high performance vehicles are gonna be traction limited. I've also upgraded to a more powerful censored brushless system, which means I expect to be traction limited. For example, let's say I wanna go 0 to 60 in 1 second. That means we need to get to 26.8 meters per second in 1 second. If we divide this 26.8 meters per second by the acceleration from Earth's gravity, which is 9.8 meters per second, we know we need to be able to pull 2.73 Gs on average the entire run, assuming we don't subtract rollout. Yes, we need to accelerate 2.73 times faster than free fall. In order to do this, we need traction, a lot of traction, and that's where downforce comes into play. The main force resisting this acceleration of the car is the inertial resistance of the car, which is equal to the car's mass times its acceleration. Our car is 8.3 pounds, and our target acceleration is 2.73 Gs, which means we need 22.7 pounds of acceleration at the wheels to actually get the 0 to 60 time we're looking for. Of course, I'm ignoring drag because at these low speeds, it's a pretty small factor, but on things like top fuel dragsters, it can become a really big deal. Luckily, this is an all-wheel drive car, so I get to take advantage of all of the weight of the car for traction purposes. If this were two-wheel drive, for example, we'd only be able to take advantage of the weight over the rear wheels, so the acceleration dynamics are quite different. The stickiest tires I own for this car have a traction coefficient of about 1.3 when they're warm, which means the max traction force that I can actually get without downforce is about 10.8 pounds. If we divide the 22.7 pounds we need by this 10.8 pounds, we see that I actually need about 2.1 times as much traction force as I'm actually gonna get. And I can't just add weight because then that increases inertial resistance, undoing what I was hoping to gain. Adding weight only hurts because it reduces our power to weight ratio. And this is where downforce comes into play because it adds traction force without adding more mass that increases our inertial resistance. And since I need this downforce to work at 0 miles an hour all the way up to 60, I chose fans. Dragsters use a bunch of glue to get their effective coefficient of friction above 4, but that's entirely impractical for road cars. My fans have to be capable of producing 1.1 times the weight of the car in downforce. And from testing, we see that these fans actually produce a whole lot more than that. They produce so much downforce, in fact, that I've been running them intentionally backwards because I don't need any margin. And I'm doing this for 3 main reasons. The first is because, like I said, the downforce was always more than I needed, so I don't need more efficiency. And the second is because it looks cooler. Obviously, this is an important factor. It was designed to look like a BT-46B or a Chaparral, not some crappy RC plane. And 3, it lowers the center of gravity a lot closer to the ground because these heavy motors are positioned lower. But you guys were persistent in demanding that I fix the orientation of these motors. Some of y'all claimed it would produce tons more downforce. Some of y'all said the efficiency would go way up, and some of y'all just called me an idiot. Either way, I tested it, and I did find out, number 1, the downforce probably isn't enough different. Both of them max out my homemade YouTube manometer, which means it's way more downforce than I need. But the second thing I did test is leak rate sensitivity, because that may matter. And I did find out that mounting them in the correct orientation does lower the leak rate sensitivity, which means I can probably increase my ground clearance a little bit to save my skirts, and it makes it less sensitive to damage to the skirts. So in this case, you guys win. I'm gonna mount them the proper way, and we're gonna see what happens. But to accommodate that, I switched to a low center of gravity chassis. Hopefully this undoes the increase in center of gravity as a result of mounting those motors much higher. I upgraded a few other things, but enough talking. Let's go see if these changes work and translate to better times. Right out of the gate, I'm gonna go ahead and be honest, this car is wildly unstable. The censored motor is an absolute rocket off the line, which makes it clear to me that the motor cogging previously was a result of using an uncensored motor. This motor also has a lot more torque, which I believe is making it easier for some of the wheels to break loose through the differential and spin the car. So to try and fix this, I'm gonna rebuild the differentials with some really thick 1,000,000 weight differential fluid to try and act kind of like a limited slip differential. And with that, let's go give it another test. And this went a little bit better, but I'm still able to break the wheels loose a lot easier than I wanted. My testing shows that I'm peaking out at 2.3 Gs, and my fastest 0 to 60 isn't even as fast as the last car. As a matter of fact, I'm having to let off throttle in the middle of the run because that's where it's losing traction. So let's go for some poor man's traction control by limiting the torque that the motor produces. I know from my motor logs that I'm pulling about 210 amps on the prior runs. And I can convert my motor's velocity constant to a torque constant to know that at 210 amps, I'm producing 0.91 Newton meters of torque. After working its way through the drive line and gear reductions, that equates to 6.18 Newton meters at the wheels. This is 54.7 inch-pounds, and then I need to subtract the torque required to accelerate the wheels themselves because those have rotational inertia as well. Dividing this by the tire radius gives us a max traction force at the wheels of 25.8 pounds. And we know from previous analysis that I only need 22.7 pounds of traction force. So let's start by limiting the traction to say 0.65 of what it was before. And we're gonna walk it up from there. Over the next 3 days, I was out at the parking lot with a laptop like I was Paul Walker or something, trying to tune this thing for max acceleration. The fan batteries lose enough voltage after about 6 runs to require a recharge, or they're gonna lose so much downforce that it's pointless to even try running. And the conditions were also all over the map. Temps in Texas swing massively, all the way from 70F down to 20F. And that means that my traction was all over the place because my tire temperature was very inconsistent. Regardless, I decided to keep pushing harder and harder until I ultimately wiped out. Our best time at this point is about 1.7 seconds, which with a rollout subtracted is 1.52 seconds. We're still not where we need to be. And that brings me to another point though, rollout. I personally think rollout is stupid on consumer vehicles. But I do need to say, you don't scale rollout for this vehicle because it's smaller. Otherwise, I would also be scaling speed. And nobody wants to watch anything race from 0 to 6 miles per hour. The major publications are literally just subtracting that first foot of their GPS data from the total time. And I understand that the staging beams that the original rollout comes from are important for NHRA events, but even top fuel dragsters use the rollout deceptively. Their front two wheels are staggered apart so that their rollout is artificially longer. And if this car were using staging beams, the rollout would be even longer than a top fuel dragster because the body is so low to the ground that the entire length of the body would be the rollout distance because it's going to hit the staging beams the whole time. And Tesla uses rollout deceptively by only applying it to the most premium models to make the time gap look much larger than it really is to their other offerings. But since I'm comparing my 0 to 60 time to consumer cars, I have to use the same annoying practice. And while I'm whining, let me just say I hate running this car. I have to charge several batteries for every single run for both the car, cameras, and the GPS. The traction is all over the map. Maybe it's because the ride height was higher. Maybe it's because it's a new skirt. I don't know. But if I just lock the differentials, it's no longer a road car. It's just a drag car, and that's not the point. Now, what about if we run the fans backwards? Can we get this thing to be a hovercraft? Kicking it around a little bit, I can tell it's a lot lighter on its feet, but not quite as light as I really expected. It definitely doesn't hover, and it handles as poorly as you'd expect. Absolute garbage, finished off the fans here as they ground on the concrete. So let's demolish all the fan-specific components to make sure I am never tempted to revive this project again. It's run its course. All right, now that I got that off my chest, let's clear up another couple of additional items. Number one, I'm doing a lot of approximations here to convey the basic relevant concepts when you're going for acceleration. As an example, tire loading versus traction force isn't exactly linear. And number two, my tire loading isn't perfectly balanced, hence the constant loss of traction throughout all the tests. As I accelerate, more mass is transferred to the rear wheels, which means the rear wheels have to take more of the load, giving the front less grip, which makes it so easy for these tires to diff out, and we're gonna lose control, obviously. I also wanna call attention to the fact that I subtracted the torque required to accelerate the wheels from the total torque available. I was using some really lightweight wheels, but if I used heavier and larger wheels like these, my torque draw from the wheels accelerating alone would have more than doubled. And I obviously didn't include the mass of the drive shafts and the gears and all that because I just assumed it was way smaller than the inertia of the wheels. But that's why it's important to limit the total rotating mass, and in some cases reduce the diameter. And lastly, when I was limiting motor torque, it was a linear limitation. If I had the ability to input that as a function, I could do some really cool stuff with other types of aerodynamics, but hopefully that's a feature we can get added later on. And if you want a great book on some of the math behind racing cars, this is probably my favorite. It has enough math to allow you to actually do some real calculations, but you don't have to be a PhD to understand it. Coming up soon, we will build an actual dragster. We're gonna create some forged carbon fiber wings, and we got a lot of other projects in works. So stay tuned and thanks for watching. If you have any questions or comments, please let me know below. Otherwise, I can't wait for the next project.